Hello, welcome back to Math 332 Linear Algebra, and this is the second video on eigenvalue and eigenvectors. In the first video, we talk about what's the definitions of eigenvectors and eigenvalue and how to find them, and also we talk about the concept of algebraic multiplicity for eigenvalue and the geometric multiplicity of an eigenvalue. And all this is important. All these things are important, and we are going to see and use them in the second video, where we talk about one of the main applications of eigenvectors, which is to help us diagonalize a matrix. All right, so this entire process is known as a diagonalization process, and the reason is very simple. So for the purpose of give you a simple example, let's stick with the 2 by 2 matrix. So we have a 2 by 2 matrix A, but everything we mentioned here apply to n by n matrices, okay? So now we have this particular matrix, which is 2 by 2. It's supposed to be pretty simple. And I'm asking you to compute what is A squared. I'm asking you how to compute what is A cubed, okay? And then A to the power of 4, so on and so forth. And maybe I can ask you, in general, can you give me a formula for A to the power of n? And this is possible. You can actually compute them, but it's going to be tedious, especially when the matrix size is big. But if your matrix A is not any type of matrix, but a special one, which is like, say, the diagonal matrix. So if you have a diagonal matrix, all these questions about d squared, d cubed, and all the way to the dn is very simple to compute. In fact, you can compute d squared and you will find out. So d squared is d times d, okay? So you take a matrix d times a matrix d, right? So if you multiply them, you will see that it turns out it'll be 1 over 2 square, 0, 0, 1 square. And this pattern persists meaning that if you do cube, so this will be 1 over 2 cube, and then 1 to the power 3. And as you can see, eventually we can show that if you do the multiplication n times, so if you do the multiplication n times, we will get this to the power of n, we get this to the power of n, because the matrix is diagonal. Diagonal matrix has this very nice property that if you keep multiplying it by itself, the end result is just basically taking the power of those diagonal entries. And so you can see that if you can turn a matrix into a diagonal matrix, it will be pretty easy in terms of computing its power. Now let's do another one. So this one is a little bit different though. So this matrix B is given by P, multiply this diagonal matrix and multiply P inverse. So here, if you look at the size, so P is a 2 by 2 matrix, and it's not just any 2 by 2 matrix, because we are assuming that P is invertible because we are looking at P inverse. So this is a product of a 2 by 2 matrix, 2 by 2 matrix, and 2 by 2 matrix. Okay, so everything here are square matrices, and if you are tasked to compute B squared, so let's do it. So B squared, so by definitions, that's P. Let's denote that as D so that I don't have to keep writing it. So this is PD P inverse. That's a B, right? Multiply PD P inverse. That's another B. So that's B squared. And because P and P inverse will cancel each other out and give you the identity matrix, which I'm going to skip. And so I'm just going to write, okay, let's do it. That's P, D, I, and then D, and then P inverse. And you can drop the I, and then now D times D is D squared, and then you have that. So B squared, okay, so B squared, so this is matrix B, and B squared will be this. All right, and you can compute again. So let's say we are computing B cubed. So for B cubed, what you need to do is you're going to multiply B 3 times. So you're going to have PDP inverse again. And what happened next is that, as you can see, this cancellation happened. Actually, we already know this is B squared. So let's write down. This is PD squared P inverse, right? We already know that. And then PDP inverse. And so again, this cancel out, and this two combine. So you have PD cube P inverse. So in general, you can see that if you have a matrix B of this form, then your B to the power of n, your B to the power of n, let's get rid of all this. So B to the power of n will be in the form of P, D, to the power of n P inverse. And what is good about this is that, again, we know that D, this is a diagonal matrix, so we already know D to the power of n. So this will be 1 over 2 to the power of n, 0, 0, 1 to the power of n. So even though this is B itself is not a diagonal matrix, but B consists of diagonal matrix in this particular form, then B to the power of n is still pretty easy to compute. Okay? All right. So let's formalize this process and give you the following definitions. So now, given a matrix A has to be square matrix, but the size doesn't have to be 2 by 2. So in general, n by n matrix, right? So A is an n by n matrix. We say that the matrix A is diagonalizable, which means you can diagonalize it. In the sense of you can find matrix P, which is invertible, such that and a matrix D, which is diagonal, such that P inverse AP will be equals to D. So that's the definitions. So a square matrix, n by n, is diagonalizable if there's a diagonal matrix such that this is true. So that means that a matrix is diagonalizable if you can find an invertible matrix P and a diagonal matrix D such that P inverse AP is equals to D. All right, so that's the definitions. Okay, so you can also write A, okay, is equals to PDP inverse. So our matrix A now is kind of like this matrix, okay? So that's the definition of a matrix that's diagonalizable. So if you have a matrix A, you can't just change it to any diagonal matrix. So because they might not, that's maybe sometimes just impossible. So we do not require, so this is one thing that you have to remember. When we say that a matrix A is diagonalizable, doesn't mean that you can take A and then somehow row reduce to a diagonal matrix. If you can do that, that's good, but that is not the definition of diagonalization. So diagonalizations means that I have matrix A, and I can find a matrix P, which is invertible, and then a matrix D, which is diagonal, such that P inverse AP is equals to that diagonal matrix D. Okay. Right. So once we know how diagonalization is defined, right, we need to talk about how do you actually diagonalize a matrix? How do you actually diagonalize a matrix? And this theorem actually tells you how to do it. So this is a very important theorem in this section. That is, if you have an A, okay, again, the matrix A, n by n, of size n by n, it is diagonalizable if and only if, so if and only if, A has n independent eigenvectors. So this theorem establishes the relationship between diagonalizations of a matrix with its eigenvectors. So it says that, okay, so again, this is a theorem which have two sides, right? If and only if. So it says that A is diagonalizable, right? A is diagonalizable, then A has n independent eigenvectors, right? So this is the directions right here. If A is diagonalizable, then A will have n independent eigenvectors. The other direction says that if you have n independent eigenvectors, then matrix A is diagonalizable. So this is a useful fact. This is much more useful if you go this way, which means that if you find n independent eigenvectors, then you can actually diagonalize that matrix A. You can make A related. In mathematical terms, actually, the proper terms is similar. Make A similar to a diagonal matrix. And actually, also, this is a theorem, which is what we call a constructive theorem, which means that when they give you the proof, they actually tells you how to do it. So they don't just tells you there exists something and something, but they didn't tell you how to find them. But this is a theorem that actually give you a constructive proof on actually how to diagonalize matrix using those n independent eigenvectors. So let's look at the proof, okay? So let's look at this directions. So assuming that A is diagonalizable, so A is diagonalizable, we want to show that A, if you compute the eigenvectors, so you compute the eigenvectors, right? If you compute the eigenvectors, you can find n independent eigenvectors, right? So let's do that. So this direction is, if A is diagonalizable, then we are supposed to find an invertible matrix P and a diagonal matrix D such that P inverse AP equals to D. That's the definitions. P inverse AP equals to D. Okay, so let's do that. A is diagonalizable, so we have that. So let's write D as this. Okay, because if matrix A is diagonalizable, the existence of this matrix, diagonal matrix D, is guaranteed by definition, right? So we have this D, right? So we write like that. So it's diagonal matrix. Let's label the entries lambda, okay? And from the notation, you kind of already see that, oh, those must be eigenvalue, but we don't know yet, okay? We don't know that yet, okay? We just know that A is diagonalizable, means that there exists a diagonal matrix D, and there exists a matrix P, all right, such that P is invertible. And we also want to write P as its column vector. So I'm emphasizing the column vectors of P. So I am writing, this is a notation. So P is a vector, it's a column vector. I have this vertical line here to indicate that it is a column vector. So we know from the definition of diagonalizations, we know existence of this matrix, and existence of this matrix, the notation here is to suggest this P is the column vectors of P. So this P is also an invertible matrix because, see, okay, P is invertible matrix by definitions also, by definition of diagonalization. All right, so now we just simply write, okay, from the definition of A is diagonalizable, right? A is diagonalizable. We know that there exists D and P such that P inverse AP equals to D. So in particular, AP will be equals to PD because you multiply P here to cancel this thing out, so you have PD. So P inverse AP equal to D is the same as writing AP equals to PD. So let's write this thing out. So AP will be A times P. This is the matrix P. We write down the column. All right, so AP, what is it? AP is A times all these column vectors, and for matrix multiplications, we know that this is the same as multiplying the column. Okay, so first column, multiply A, you have AP1, and then AP2, and then all the way to APN. Okay, so A times P, if you write out the P as is, matrix P as is a column like that, then we know each of the column on the product of AP will look like this. This is matrix multiplication property that we learned in the first week of class. Okay, so we compute the AP already, and now we compute PD. So P times D. Again, I'm writing the column of P. This is the column of P, and multiply D. And if you multiply out again from matrix multiplications, if you remember, let's say we multiply this part. This is going to be lambda 1 times P, and then 0 times this, and then 0 times this. Right? So you know, let me say that again. So this is again matrix multiplication property. So when you multiply this matrix with this column, you will take lambda of this, okay, plus 0 times this, which is 0, plus 0 times this, which is 0, all the way to 0 times this. So the first column in PD, will be lambda 1 P1. Same thing. If you take this, multiply this matrix, you will get lambda 2 P2. So P times D will give you a matrix that looks like this. So now we computed AP and PD, so they are supposed to be equal from the definitions, from the assumption that A is diagonalizable. So when you equate them, AP and PD, when you equate them, this is AP. Let's look at this again. This is AP, this is PD, and since they're equal, this column must be the same as this column, right? Let me say that again. So this matrix and this matrix is the same. So this column will be the same as this column. This column will be the same as this column. This column will be the same as this column. So we get AP1 equals to lambda P1, AP2 equals to lambda P2, all the way to APN is equal to lambda PN. That, my friend, tells you that P1 is an eigenvectors with corresponding eigenvalue lambda 1. P2 is actually an eigenvectors with corresponding eigenvalue lambda 2, and so on and so forth. So the conclusion is that if your A is diagonalizable, that means that there exists matrix P and D such that P inverse AP equals to D, right? Such that P inverse AP equals to D, right? So by the assumption P inverse A is diagonalizable, that means exists D, exists P, which is invertible, such that P inverse AP equals to D. Then the column of P. The column of P is actually this column, all this column, P1, all this column, P2. The column, okay, of the matrix P, is actually the eigenvectors. The eigenvectors. And the diagonal entries of the diagonal matrix is actually the eigenvalue. This is actually the eigenvalue. So we have shown that if A is diagonalizable, this is right here, A is diagonalizable, we have n eigenvectors. We have n eigenvectors. We haven't shown independent yet. We show that there are n eigenvectors. What are those n eigenvectors? These are the n eigenvectors. How do you know they're independent? How do you know that this column vectors is independent? Well, you know that they're independent because if you put those vectors as a column of P inverse exists. P itself is invertible. If P is invertible, the column of P has to be linearly independent. If your column of P are not linearly independent, you can invert that matrix. Think about it. With all the information you learn on column space, dimensions, and everything, basis, you should be able to see that if your column of P are not linearly independent, then your P is not invertible. And with P invertible, that will imply that the columns are linearly independent. So we actually have shown, that if you have this one part of a theorem, so if your A is diagonalizable, then you will have n linearly independent eigenvectors. Now we want to do the opposite, which is the other direction now, which is actually more important, which is like, hey, if you have n linearly independent eigenvectors, how do you show that A is diagonalizable? And for that, the trick is not very difficult either, okay? So let's look at this slide right here. So now, as I said, for the more useful directions, suppose, so these are hypotheses now. Suppose we have n independent eigenvectors, right? And we label them P1 all the way to Pn. So now we start with n. We have n, okay, not just eigenvectors, but linearly independent, okay, linearly independent, right, eigenvectors. So this is the hypothesis. So these are the hypotheses. So because we are assuming that we have all these eigenvectors, so these are the eigenvectors, and every eigenvector has a corresponding eigenvalue. So let's, for notations, right, for simplicity of notations, let's call the eigenvalue for those eigenvectors P1 lambda 1. Let's call this eigenvectors P2. This eigenvalue is lambda 2, so on and so forth. Now, I want to show that having this, okay, and also they are independent. Having this and all the P are independent, I will be able to diagonalize a matrix. Meaning what? Meaning that I should find a matrix P, I should find a matrix D such that P inverse AP equals to D. So to diagonalize a matrix, I need to show that that is an invertible matrix P. Not just P, the P has to be invertible, and a diagonal matrix such that P inverse AP equals to D. That's the definition of being a matrix being diagonalizable, right? So assuming that we have n independent eigenvectors, I want to show that I can able to do this. So I need to construct a matrix P. I need to tell everybody what is my matrix P, and also I need to tell everybody what is my matrix D. And not just telling everybody that I have a matrix P and I have a matrix D, I also need to show it to everybody that with this matrix P and this matrix D, I will have P inverse AP equals to D. All right, so now I'm showing you, okay? So now I'm showing you, I'm giving you a constructive proof, which means that, hey, since you have all these eigenvectors, why don't you take all these eigenvectors, okay? These are eigenvectors, right? In the form of this, right? This is going to be like n by 1. All these eigenvectors going to be n by 1. It's like column vectors. So I say I'm going to construct my matrix P by putting all the eigenvectors as the column of that matrix. So that's my matrix P. That's my matrix P, okay? Now, and I am actually going to take D, okay? I'm going to take my D as the diagonal matrix, which has all these eigenvalue on the diagonal and everything else is 0. So I'm going to take P, this P, I'm going to take this D, and then I'm going to show it to you that with the P and D, I have P inverse AP equals to D, okay? All right, so again, the trick is not to show this directly because I can't really do P inverse, right? So P inverse AP equals to D. So the trick is instead of showing this, I can show this first. So let's show this. So again, let's show this, okay? Let's show this. So again, multiply A times P. Same as before, multiplies A times P. So this is the product of AP, okay? And because all the P here is eigenvector, so AP1, so this first step is the same as before. Like this is this first step right here. This is just matrix multiplications, okay? Nothing to do with fancy eigenvectors. Okay, so this is just matrix multiplication. But my P here, my P is a special P. So my AP1 will give me lambda 1 P1, my AP2 will give me lambda 2 P2, and all the way to APN will give me lambda n PN. Okay, so this matrix is actually can be written as the product of these two matrices. As a product of these two matrices. So lambda 1 times this equal to this, right? Same as before, you can check. So this is actually equals to this. So the way, because of the way I name my P and D and so on, so I have now AP equals to PD, right? So I have now AP equals to PD. That's what it said. AP equals to PD. Now my P, okay, they are independent. They are independent. Why are they independent? That's from the hypothesis. Okay, those eigenvectors are independent. There are n of them, and they are independent. So independent column. These are all independence column. So this matrix is invertible. So this matrix right here is invertible. So I'm writing P inverse AP equals to D. That's the definition of A being diagonalizable. So now I have proven. So I have proof that we go through the proof to shows that if you have n independent eigenvectors, you can diagonalize the matrix. You can diagonalize the matrix. So the end of the proof. This is the end of the proof of this theorem. Okay, so this is a very nice theorem because okay, it actually tells you how to construct. Okay, they say that this directions. Okay, if your A has n independent eigenvectors, okay, if your A has n independent eigenvectors, then your A is diagonalizable. They don't only just tells you that, they actually tells you how to do it. How to do it. Okay, let me summarize it here. Okay, so suppose you have n independent eigenvectors. Okay, how do you diagonalize a matrix? Well, you construct P by putting your eigenvectors like this, right? And then you construct D by putting the corresponding eigenvalue like this, right? And then definitely P inverse AP will be D. Okay, right? So if you have n independent eigenvectors, put the n independent eigenvectors as a column of P, and then construct matrix D like this, then you will have P inverse AP equals to D. Okay, let me show you some example. Okay, so you have a matrix A. Okay, you have a matrix A. All right, we want to diagonalize that matrix. Okay, we want to diagonalize that matrix. And I suppose I already know P1 is an eigenvalue. Sorry, if I already know P1 is an eigenvector corresponding to this eigenvalue, I know P2 is an eigenvector corresponding to this eigenvalue. Then, if I put my P, if I put my matrix P as, see here, take the column, this column, and put it here. Take this column P2 and put it here. Then, right, then take your D. Take your D as -4, 0, 0, and 7. Then, by the theorem, okay, by the theorem, we know that your A, this A, right, you know that if you do that, by the theorem, okay, you will know that this matrix A, right, P inverse AP will equals to D, which means that this matrix A is diagonalizable. All right, diagonalizable. Okay, it is not A is not a diagonal matrix, but it's connected to a diagonal matrix like this. And we already seen that having this form is good because having this form is the same as saying I have PDP inverse. That's your A. And I can compute A to the power of n. A to the power of n is PD to the power of n and P inverse. And this is easy to compute. So I will be able to raise the power of the matrix. You might not be you'll be like, you might not be impressed. You'll be like, dude, okay, so what? Like, I have a matrix A. I can raise it to the power of n, and that's an easier way to compute that. So what, right? Why do I want to raise the power of a matrix? Well, that answers will be addressed. That question will be addressed in the third video. There are a lot of applications that depending on how you raise the power to of a matrix. All right, so one of the example will be example where if you have taken differential equations, which is 252, you will see how all this information, all these pieces fall together and give you a very nice proof on how to solve a system of linear differential equations. So that's that, okay? So that's that, okay. So now the problem, that's a big problem here. That's a big problem here. We know a lot of stuff. Everything we know so far is good, it's true. that, hey, I know how to diagonalize matrix. If you have matrix A, if I can have, okay, if I can have an independent, okay, eigenvector. If I have that, cool, I can diagonalize the matrix. Now, the question now is, what if you don't, right? What if you don't? What if you don't have n independent eigenvectors? Then then we'll be in trouble. We'll be in trouble. Okay, so the next theorem and the last part of this video is try to address the questions like, wait, how do we diagonalize a matrix if we don't have enough eigenvalues, eigenvectors, and how do we know which one is which? So here's the trick. Here is the part where you have to review and recall the terminology we established in the first video, which is algebraic multiplicity and geometric multiplicity. Okay, so a quick review. If you compute, right, if you compute determinant of a minus lambda I and set equal to 0, you have a polynomial in lambda, right? So you have a polynomial in lambda. So let's say you have, and then you factor them. So let's say this is what happened, right? So this is what happened, let's say. So let's say your A is a 4x4 matrix, right? And the characteristic polynomial looks like this. So lambda equals to 1 has algebraic multiplicity equals to 3, because algebraic multiplicity is the number of times that eigenvalue appear in this factor. That's easy. Geometric multiplicity, you will have to compute the eigenspace and look at the dimension of the eigenspace. Okay, so lambda equal to 2 is an eigenvalue, and the algebraic multiplicity is 1 because it appears only one time, and the geometric multiplicity will be 1. This is straightforward. This is always the case. But the problem is, so let's look at the theorem, right? The theorem before. So the theorem before says that this is a 4x4 matrix. So I need 4 independent eigenvectors. I need 4 independent eigenvectors to diagonalize it. So I have 1 independent eigenvectors here, which is coming from here. But this is the problem. This is the problem because this lambda equal to 1 appear 3 times. But the eigenvectors coming from this eigenvalue, you might only have 1 eigenvector. So let's say the geometric multiplicity is 1. Meaning that the eigenspace for lambda equals to 1 consists of only 1 independent eigenvectors. Then you have 1 from here and 1 from here. You only have 2 independent eigenvectors. We need 4. We need 4 to do that. We need 4 to do that. All right. So we also know from the previous video, this can actually happen because the geometric multiplicity is less than or equal to the algebraic multiplicity. So when you have repetition like that, you might not have enough eigenvectors. Like you do not have enough eigenvectors. This is 1, this is 1, you only have 2. Let's say the geometric multiplicity is 2, which means that the eigenspace, the basis for the eigenspace, the basis for this eigenspace, so if you look at the basis, it has 2 vectors. So you have 2 vectors for that. So let's call it P1 and P2, whatever. So you have 1 vector, 2 vector, 3 vector. You still don't have enough. So you only have enough eigenvectors to diagonalize a matrix if this geometric multiplicity is also 3. Meaning that if we repeat 3 times in the characteristic polynomial, you better make sure they give you 3 independent eigenvectors. Otherwise, you would not have enough eigenvectors. So algebraic multiplicity, if it is not 1, if it is more than 1, like here, 3, then your geometric multiplicity have to better match with this. Otherwise, you would not have enough eigenvectors. That is what this theorem tried to tell you. This is what that theorem tried to tell you. It says that a square matrix A is diagonalizable if and only if the geometric multiplicity of every eigenvalue is equal to the algebraic multiplicity. The problem is exactly this. If you have algebraic multiplicity is 3, and if you have geometric multiplicity 1, then we are screwed because right now, this gives you 1 independent eigenvector. This gives you 2, another one. So you have 2. We need 4. All right. So that's the thing. So this theorem tells you under what circumstances your matrix is diagonalizable. Well, you better make sure the geometric multiplicity and algebraic multiplicity matches. So for example, so this matrix has characteristic polynomial like this, right? Okay. So your lambda equals to -1. Okay. So here your lambda equals to -1 and your lambda equals to 2. Right, so your lambda equals to -1 have algebraic multiplicity 2. So this is the problem, right? And this has algebraic multiplicity 1. But we already compute from before, okay? We actually already compute from before. Sorry, we already compute from before. This eigenvalue if you compute the eigenspace, you actually find 2 independent eigenvectors. So the geometric multiplicity in this case is 2. You have 2 vectors right here. And if you compute this, you also have 1 basis in this eigenspace. So taking this, this 1, 2, and take this as the third one, you actually have 3 independent eigenvectors, okay, to diagonalize the matrix. Right. Right. So here, so you have 2 from here, right? Take this 2 and take this one, which is this one. Then your P, you have enough independent eigenvector. You can have a P1, P2, and P3. We have enough because this is a 3 by 3 matrix. I need 3 independent eigenvectors, and I found all 3 of them because the algebraic multiplicity and geometric multiplicity matches, meaning that when this thing appears twice, it also gives you 2 independent eigenvectors. So it matches. We have enough eigenvectors, but sometimes you don't have that. Okay, so once you have that, you can put it like that and you get all the answers that you want. Okay, you can diagonalize the matrix, but sometimes you don't have that. The example that we have from last video is that you have this case now, lambda equal to 2, lambda equal to 4. This one have algebraic multiplicity 3, which means you lambda equal to 2 repeats 3 times, okay, in the characteristic polynomial. Okay, this one here, algebraic multiplicity is 1. But you see, this eigenspace, if you compute the eigenvectors for this, you only have 1 basis. The geometric multiplicity is 1. It's not enough, so I only have 1 here. And then here I have another one, right? I have 1 here, and then I have another one, so I only have 2. By the theorem, I need 4. I need 4 independent eigenvectors to diagonalize it. So now I don't have that. So therefore, you will have to conclude that, oh, matrix A is not diagonalizable. It's not. Why? We don't have enough eigenvectors. Why? Because even though lambda equals to 2 repeat 3 times, they don't give you 3 independent eigenvectors. They only give you 1, because if you compute the eigenspace, this is the only thing you get. So that is the end of this sections where we talk about what is diagonalizations means, why does it matter, because we want to raise the power, and how do you actually know when you can diagonalize a matrix? Well, it depends on the eigenvectors. You have to have enough eigenvectors. And then we talk about in what circumstances we might not have enough eigenvectors. Okay, so that's the end of this video. And then the third video, we'll look at the applications. Like why? Like why do you want to raise the power of a matrix? All right, thank you very much for your attention.